All right, so now that we have taken our test on derivatives part one and had a lesson on higher order derivatives, we can start to kind of bridge from our last test into this new concept. Um, so to get going here, first thing I want to talk about is some notation. We don't want you to get hung up on notation. There are several different ways that we can represent derivatives. Here we've got our first derivative, second derivative, and our third derivative. So just kind of notice right here, our notation for primes, this would be f prime of x, the first derivative, y prime, the derivative of y with respect to x, or just the derivative with respect to x. So for our second derivative, we would call this f double prime of x, or y double prime, or the second derivative of y with respect to x. And same thing here for our third derivative, f triple prime, we could say, of x, y triple prime, or the third derivative of y with respect to x. So, this is different notation we can use to represent that we're finding higher order derivatives. Okay, so what we're going to take a look at here, I'm going to model a couple of examples of some problems that were very similar to problems on your test. And so our objective is to kind of correct issues from the past while extending our knowledge of the present. So we're going to take a look at a problem very similar from the test, several of them. We're going to find the first derivative, the second, and then ultimately the third derivative. Okay. So in our first example here, first thing we'd want to do would be to write our function as 5 take away 4x to the 1/2 power, the preparatory line there. So y prime would equal 1/2 times 5 minus 4x to the negative 1/2 times, and then we're going to go inside and catch the derivative of that 5 minus 4x, negative 4. So to clean this up, we would look at having 1/2 of negative 4 is negative 2 times 5 minus 4x to the negative 1/2. And if we wanted to give the derivative, our final answer in a simplified version would be negative 2 over the square root of 5 take away 4x. There's our final representation of our first derivative. Now, if I'm needing to proceed into a higher order derivative, it's not advantageous to use this format. We actually want to backtrack a line of work and use this line of work right here to proceed with our higher order derivative. So we'll say then that y double prime is equal to, and what you'll notice is we actually get to basically replicate the same rule that we did initially. That being the power rule with a little bit of a chain attached. So we've already got our negative 2 out front. We're going to bring down that negative 1/2. And we've got 5 take away 4x raised to, then here we drop back a power, so that'd be a negative 3/2. And then times that negative 4 again, the derivative of the inside. Cleanup would look something like this. Let's see, negative 2 times negative 1/2, well, that's just 1. And 1 times negative 4 there is going to be negative 4 times 5 minus 4x to the negative 3/2 power. And once again, if I want to write my final answer here, we'll say y double prime is equal to negative 4 over, let's see, that's going to be the square root of 5 take away 4x quantity cubed. There would be our final representation for our second derivative. Negative 4 over the square root of 5 minus 4x cubed. And yet even still, let's say we want to go another higher order derivative. Well, same thing. We want to stick with that line before. It's not advantageous to use this. Here we'd have to do a quotient rule. The work could get pretty messy and the cleanup could be even messier. So we'll just stick with the repetition of the same power and chain rule happening. We'll venture over here to our third derivative. So we've got a negative 4 out front already. Negative 3/2 power is going to come down. And then we'll go 5 minus 4x. All right, so negative 3/2 take away 1. Let's see, it's going to give us a negative 5/2. And let's do some cleanup here. Y triple prime is, all right, so negative 4 times negative 3/2. Well, negative times negative is a positive. 4 divided by 2 is 2, and 2 times 3 is going to yield 6 times 5 minus 4x to the negative 5/2. Or final answer, our third derivative is 6 over, let's see, that'll be the square root of 5 take away 4x all to the 5th power. So you'll notice that as we venture into higher order derivatives, sometimes it's actually a little more useful or helpful to actually not use the simplified version as we venture into those higher order derivatives until we get to the derivative that it is that we want. Okay, so this problem is very similar to the one from your test, and we're actually going to make some connections here on the back side as we venture forward. Let's clear that out right there. All right, so let's scroll down here to number 2. We're actually going to work 2 and 3 here. These will be all the ones that I work with you, and then you guys are going to take over with the back side. So to find our derivative here in number 2, let's see, let's go blue. The first thing I want to do is a nice little preparatory line of work. I could do a quotient rule here. There's nothing wrong with that, but it's much more difficult, I think, to find that derivative. Let's write this as a product. Let's write that as 3 times 4x minus 1 to the negative 2. So you notice we've kind of got this constant times a function right here where we're going to have to do a power chain rule. So let's go first derivative. It's going to be negative 6. That's that 3, and the negative 2 comes down, multiplies. 4x minus 1, drop it back a power, and then go inside and catch the derivative of 4x minus 1, which is just 4. So our first derivative could be represented something like this. We call that negative 24. That's that negative 6 times 4 there, over 4x minus 1 cubed is our first derivative. And let's say that we wanted to find the derivative of that. So once again, if I leave it the way I've got it bubbled, I'm going to have to do another quotient rule. Let's pick up right here with this line of work and say that our first derivative is equal to, let's call that negative 24 times 4x minus 1 to the negative 3. And I can actually derive the power chain rule here. We've got this constant times a function that requires the power chain. So let's go second derivative is going to be, all right, so I'm going to pull that negative 3 down and multiply it there and then take 1 back from it. So you're looking at negative 3 times negative 24, I believe that's 72. 4x minus 1 to the negative 4 power, and we'll times that as well by 4, the derivative of the inside. So you'll notice that we keep catching, the derivative of 4x minus 1. Each time we find that derivative, that chain rule is still present, and we could give our second derivative, let's see, what's 72 times 4? 72 times 4, I believe that's 288, so 144 double is 288, 288 all over 4x minus 1 to the 4th. There's our nice second derivative, higher order there. And of course, we'll venture one step further. Let's take that over here to our third derivative. We'll say, let's go second derivative first. Let's get a little preparatory line of work here. That's 288 times 4x minus 1 to the negative 4. And it's the same rule, guys. It's a constant. There's that power chain. We're going to bring that negative 4 down. F triple prime of x is going to equal, I need my calculator a little bit here, times negative 4, negative 1,152. 4x minus 1 to the, we'll drop it back a power, and then times that by 4. Okay, so we'll give our third derivative as, let's see, what's that times 4 as well? Negative 4,608 all over 4x minus 1 to the 5th power. It's a nice third derivative there. So, higher order derivatives may seem a little work involved, but it is something that we're expected to know how to do. And so, recognizing the ease with which we can do this, I think, alleviate some of that pressure of having to do all this work. Like, it would have been a lot more work to have gone quotient rule and quotient rule and quotient rule there, getting all those simplified and not making mistakes. So I think that this is a much easier route to go here. Okay. All right, so we're going to finish one more here. This is one that's also similar to one from our test. I do have a little typo right there, and we'll fix that here in a second. But let's throw in the natural log into the mix and some trig, and let's do some higher order derivation. So that should be x right there, cosecant of x right there. All right, so let's go first derivative. So y prime is going to equal, so when we derive natural log functions, it's 1 over what's on the inside And then we're going to catch with our chain rule, and I'm going to come underneath here. I didn't leave myself much room. The derivative of cosecant plus cotangent. So the derivative of cosecant is negative cosecant of x cotangent of x. And then derivative of cotangent is negative cosecant squared of x. Okay, there's our chain rule, the derivative of what was inside of the logarithm. Let's write that down. A nice big line of work here. Negative cosecant of x cotangent of x minus cosecant squared of x all over cosecant x plus cotangent x. Okay. And some of you may have gotten this far on the test, but maybe you realize that, hey, this answer is not there. So what, did I do something wrong, or is there something I can do to simplify this? There's nothing that we've done wrong here. We just need to look at a simplification. Let me grab me a highlighter here. Let's go through. If you look in your numerator, you'll notice that there's a negative cosecant and a negative cosecant present in both of those two terms up top. We can actually factor that negative cosecant of x out, and it leaves us with cotangent of x plus cosecant of x. And as we kind of write our denominator down, hopefully something's, a little light bulb's going off in your head there of, hey, check this out. We can actually divide out this cotangent plus cosecant with this cosecant plus cotangent. So our derivative actually simplifies to be something pretty nice. It's just negative cosecant of x. There's our first derivative. Some of us may have not thought to, perhaps on our test, to have divided that out up top and to simplify our trigonometric piece. There's a nice first derivative. So venturing into our second derivative, is actually just going to be a rule. If y prime is equal to negative cosecant of x, then y double prime is equal to the opposite of, and then we're going to derive cosecant. That's negative cosecant x cotangent x. Okay. So our second derivative is just a positive cosecant x cotangent x. Oh, nice. That was one of the easiest second derivatives we've done so far. All right, so let's finish out here with finding the third derivative of this, and we'll kind of point something out as I write this second derivative down here. This is the cosecant of x times the cotangent of x. So as we do our third derivative, we'll need to follow a product rule. Y triple prime is equal to, all right, let's go derivative of the first. I'm going to put this in parentheses. So negative cosecant x cotangent x times the second, plus the derivative of the second, come underneath the line right here, derivative of cotangent is negative cosecant squared times the first. Here's our product rule. We don't have any composition here, so we don't need to worry about any chain rules. It's just x on the inside of these trig pieces. And let's see what we can do with our answer here. Let's see if we can't consolidate that a little bit. That's going to be negative cosecant of x times cotangent squared of x. And we're adding a negative, so I'm just going to go minus cosecant squared times cosecant. It's going to be cosecant cubed. I think that's a valid representation there of our third derivative, but maybe a factorization here. We could maybe look at pulling out a GCF of negative cosecant. Let's see what that looks like there. That leaves us with, let's see, cotangent squared of x plus cosecant squared of x. You might be tempted to want to look on the inside of those parentheses and say, hey, isn't that a Pythagorean identity? But then we'll recognize that it's actually 1 plus cotangent squared equals cosecant squared. So we're running into a little bit of an issue with maybe applying a Pythagorean identity there. So we'll just leave it as this. So higher order derivatives, making some connections to problems similar to the test, taking what was troubling us and maybe being a little bit better. Maybe we were initially struggling with finding these initial derivatives, but now that we maybe see an easier route, these higher order derivatives don't seem as daunting. All right, let's clear that off, and let's go through and talk about what it is that I want you guys to do to kind of follow up today. So there's two objectives that you have for Friday and Monday while I'm gone. Friday and Monday, you got basically the same assignment. The first assignment would be to do your test corrections. So separate sheets of plain white paper, work them in order, please. You're going to show me every problem that you missed, rework it, find the derivative, show me how it leads to the correct answer, and you'll staple your corrections to the back of your test, and you'll submit that into the basket. And let's try and do that at the conclusion of the period on Monday if we can. Okay. In addition to that, we want to work on this little assignment as well. So you're going to work these on a separate sheet of paper as well, and you're going to put your answers in a box, your final answers in a box. That'll make it a little easier on me to grade them, to find your answers. But you're going to need to reference your test to do these. Okay. So for example, for this first problem, you're going to go to problem number 2 from your test. And if you miss that one, we're assuming you've already corrected it with your corrections, and you're going to pick up with that correct derivative, and you're going to find the second and the third derivative of the function in problem number 2. So there should be 2 answers there. The second derivative of that function is this, and the third derivative is this. And you're actually going to repeat that very similar process for several different problems on the test. You're going to do problems 2, 3, 4, 6, 8, 9, 14, and 16. You're going to go and grab those functions and find some higher order derivatives, the second and the third derivative. Box your final answers, please. This is a separate assignment from the corrections. In addition to those 8, you're also going to work on these 2 particle motion problems. We talked about, why do we have higher order derivatives? And it's because it establishes a wonderful relationship between position, velocity, and time. So we got a couple little multiple choice problems here involving higher order derivatives for some multiple choice formats. Okay. So we will also submit this little assignment. This is something I want you to staple this actual sheet of paper to the 10 problems with their work, and we'll submit these on Monday as well. Okay, so once again, to be very clear, test corrections are due end of the period on Monday, as well as this follow-up assignment right here, due at the end of the period on Monday. So use your time wisely in class on Friday. Sorry, the bell's ringing. Use your time wisely in class on Friday. Use your time wisely in class on Monday. If you need to work on this over the weekend, then do so. But we should be ready to turn this in at the end of the period on Monday. On Tuesday, you're actually going to have another similar lesson where you're doing some different derivatives with me, and we'll pick up with that on Tuesday. Thank you, guys. I miss you.